Hello students, welcome back to the lecture. We will continue with our discussion on UV visible spectroscopy, and then we will go to look at the applications. In the last lecture I discussed about how to calculate energy of various electronic levels associated with conjugated molecule. Today I will focus on how to know the energy of different electronic orbitals of electronic materials. So, modeling an electronic material as a box allows us to ignore atoms. So, again we are going to apply the concept of particle in a box to model electronic materials. Here the boxes can be of different dimensions. Quantum wells are known as two dimensional. I will explain what I mean by two dimensional in the next slide. The quantum wire is modeled as one dimensional material and quantum dot is considered to be 0 dimension. Now, let us discuss about what is quantum dots. Quantum dots are semiconductors that are on a nanometer scale, and as the name suggests, they obey quantum mechanical principle of quantum confinement. They show energy band gap that tells you about the wavelength of electronic transition, either it is related to absorption or emission spectra. What you will find out is that the absorption and resultant emission wavelength is dependent on the size of quantum dot, and that can be explained on the basis of modeling it as a particle in 1 or 2 dimension or 3 dimension. So, what does the level quantum means? Quantum level basically refers to confinement of atoms. So, when I say that quantum dot is 0 dimension, what I mean is that the quantum dot is confined, the material is confined in all 3 dimensions. Why does this 0 comes? Because it is unconfined in any of the dimension. You take x dimension, y dimension, z dimension, it is unconfined in all 3 directions, or in turns it means that it is confined in all 3 dimensions. Now, what we mean by confined? When we say an electron is confined, we mean that critical dimensions are on the order of the wavelength of an electron. And what is the result of it? Result is when particles are confined, their energy levels become discrete. That is what I have shown in the last lecture. So, confinement results into energy level becoming discrete. So, now let us again discuss what I mean by quantum well, what I mean by quantum wire, what I mean by quantum dot. Now, look at this figure. This represents quantum well and it is called 2 dimensional material. 2 dimensional means it is unconfined in 2 dimension. So, if you look at this picture, it is unconfined in x dimension and it is unconfined in y dimension. where it is confined is in z dimension. So, this is very small. Okay. This is your quantum well. So, if you can look at here, this size is very small. Okay. How much small, that I already discussed with you, that its critical dimension must be on the order of wavelength of an electron. So, that you need to keep in mind. So, wavelength of electron is the key. So, in the z direction it is of the order of wavelength of electron. So, again 2 dimension means it is unconfined in x direction, y direction, it is confined only in z direction, and that kind of material is known as quantum well. What is quantum wire? Now, you see this is called 1D material. What does that mean? It is unconfined in one dimension. What is that dimension? That dimension is z here. So, you can see Lz is quite big, whereas the Ly and Lx is very small, of the order of wavelength of electron. So, your quantum wire is confined in y direction, confined in x direction, but unconfined in z direction, and that is why it is known as 1D material, because it is unconfined in one dimension. Quantum dot, in all 3 directions it is confined, because length in all 3 directions is of the order of wavelength of an electron. So, this is known as 0 D, because here 0 stands for the direction in which a material is unconfined. Since material is confined in all 3 directions, so there is no direction in which material is unconfined. So, now let us discuss about quantum well. As I told you that quantum well confines electron in one dimension, in this case it is your z direction, and so the energy will take discrete value, and this is your diagram. So, this is your x axis, this is y axis, and this is z axis, and in the z axis you have discrete energy levels. So, how I can write the energy of quantum well? Energy of quantum well will be the sum of energy in x direction, energy in y direction, and energy in z direction. And since in this direction, in the z direction, the material is confined, and so its energy will be given by n square h cross square pi square by 2 ml square. That is what is the energy, or you can simply write n square h square by 8 ml square, 8 ml square. This is when this is in the dimension in which your material is confined. For other 2 directions, there is no limit on value of this k, kx and ky, it can take any value. And so, in these 2 directions, your energy is going to be continuous. Only in this direction energy can take discrete value. For quantum wire, since it is confined in 2 directions, it will depend on 2 quantum number, nx and ny, nx and ny, and nx and ny can only have value 1, 2, 3, 4, and your quantum wire is confines electron in 2 dimension, and that is your energy level diagram. For quantum dot or nanocrystal, since it is confined in all three directions, so it will depend on 3 quantum number, that is n, m, l, and your equation will be this, and the wave function can be written in terms of psi is equal to phi z phi y multiplied by phi x, phi z multiplied by phi y multiplied by phi x. For quantum wire confined in 2 directions, and so depends on 2 quantum number n and m, and your energy will be given by these 2 terms, and this is where it is not confined, and your wave function will be phi z multiplied by phi y and exponential I k x into x. In quantum well, it is confined in only one direction, that is z direction. So, it will depend on n only, the energy will depend on n only, and your wave function will be given by this equation. So, this is the way you can model an electronic material. Now, let us think of how the evolution of energy levels takes place from a hypothetical diatomic molecule to a bulk semiconductor. So, what happens if suppose there are 2 atomic orbitals which combine to give 2 molecular orbital, for example, HOMO and LUMO. This is one molecule of 2 atoms, or you can say one diatomic molecule. If you take 2 diatomic molecule, you will get this kind of a structure. If you increase the number of molecule, then what will happen, that here there will be kind of energies are overlapping with each other, energy is overlapping with each other, and that is when you have a nanocrystal. And when you go to bulk, you have a LUMO looks like this and HOMO looks like this. Now, HOMO is known as valence band and denoted by VB, and LUMO is known as conduction band, and the gap is given by E0 naught. In nanocrystal, this is the way LUMO looks like, this is the way HOMO looks like, and the difference between this is given by Eg and C. Now, this is your energy profile for a nanocrystal or bulk semiconductor. So, this is energy versus density of a state. So, if density is low, you have a two energy levels, and when you have a nanocrystals, you have something like this, and if you have a bulk semiconductor, you have occupied level here, unoccupied level here, and the difference between 2 levels is known as band gap, and band gap will depend on the size. This is simple if you look at cadmium, selenium nanocrystal. So, it will look like this. So, if we look at quantum dots, what we can see is the emission and absorption spectra corresponding to the energy band gap of the quantum dot is governed by quantum confinement principle in an infinite square well potential, and the energy band gap increases with decrease in the size of quantum dot. So, now let us look at here. What is E1? If you remember, this is n square h square by 8 ml square, and let us write this as E1, because for n is equal to 1, your h square by 8 ml square is equal to E1, and so En, let us write En is equal to n square. So, this is your En. So, I can write En is equal to n square into E1, since E1 is equal to h square by 8 ml square. So, if n is equal to 1, so it is simply E1. If n is equal to 2, you have a 4 E1, and n is equal to 3, then you have a 9 E1. Now, let us look at, if I increase the size of your quantum dot, what will happen? So, when I increase the size, you see here I am going from this size to this size. So, certainly this size is larger. So, in that case, if you remember, E1 is equal to h square by 8 ml square, and since L is high, L is large, and so E1 in this case is going to be small compared to E1 in this case. And now you see, so E1 r is going to be smaller than this, and this 4 E1 is going to be much smaller than 4 E1b, and so gap between two energy levels will be small. Gap between two energy levels will be small when you have bigger quantum dot. What does that mean is that if delta E is small, it means lambda will be large. And so, if we are going from a smaller quantum dot to a bigger quantum dot, what you will get is something like this. Color will change from blue to red. Red means bigger dots and blue means smaller dots. So, this is your smaller dots, this is for smaller and this is for bigger. So, as the size of quantum dots increases, you move from smaller lambda to higher lambda, means you are going from blue to red. So, this is the way you can explain the color of quantum dots, and again that you can show by the energy profile. So, here is conduction band, here is the valence band. When this is small, then you see the red color, when this is large you see blue color, and red you get when the size is big, blue you get when size is small. So, if quantum dot size is big, then energy gap is small and lambda is high. When the quantum dot size is small, then energy gap is larger and lambda is smaller. So, this is about the way we explain the color of nanocrystals. Now, we will go and look at the experimental setup. So, in the experimental setup, there are two very important component. One is your light source and another is monochromator. So, first light source goes through monochromator and then it passes through sample, and sample absorbs some radiation, the rest of the radiation is detected by a detector. So, what is happening, that light crosses through your sample. When light crosses through the sample, the intensity of the light will decrease from I naught to I, and this is because a part of the light will be absorbed by the sample in a cuvette. And what we do is, we measure this intensity, we already know I naught, and based on that we can calculate what is a physical parameter known as absorbance. There can be various type of spectrophotometers, fixed and variable wavelength, single, split and double wave. Cuvettes are these. So, you can use glass or plastic cuvette for visible region, but not for UV region. Quartz is needed if you want to measure in UV. You can sometimes use acrylic also if you want to measure in UV region. Now, one of the important part is monochromator. What monochromator does? So, what monochromator does is, you see here is your light. Light is first reflected by this mirror, and then this goes to this D, and what it does? It basically split this light into various wavelength. You again keep a mirror, and now what it is doing? Just look at it. What it is doing is that all, for example, this color, or let us take all green color. So, green, green and this is green. Okay. All three green color is now comes and meets at one point, and this is the way you are able to select a particular wavelength. All this pink one will come at one point, all this whatever this color is violet, it comes at one point. So, what is being done is, first light from the source is reflected by mirror, then it is split by a grating, and then again it falls on a mirror. What it does is it splits the light into different wavelengths light. Okay. So, and now here is a detector. Now, what you can do is, depending on the wavelength at which you want to look at, the absorbance, you can just move the detector. So, sometime first you can look at the green one, then you can look at blue one, and then so at every lambda you can look at what is the absorbance. At every lambda you can look at what is the absorbance, and this is the way your spectrophotometer works. So, light source, lens, then it passes through monochromator, which is either in form of prism or a grating. What it does, as I told you, that it will split the light into various colors. You select one of them using slit, which is basically acts like wavelength selector. So, you can move it. So, you can select, for example, in this figure yellow light has been selected, but if you move it down, then it will select the green light, and so on. You pass through sample solution, and what you get is intensity after the absorption of it in sample. Now, these two things we know, and based on these two things, digital display will tell you about absorbance. Now, I will discuss about what is absorbance. So, the numerical expression of absorbance is given by Lambert's Beer law. So, now look at, this is your suppose cuvette, this is your cuvette, and then cuvette containing sample, and then what happens that you are sending light whose intensity is I naught, and when this light passes through sample, it gives you intensity I. Rest of the intensity is absorbed by the sample. So, let us think about a small, very infinitesimal volume in this cuvette. So, let us think about that, if I here I intensity and that changes to I plus d I when it passes through this sample, this small volume, and the length of this is d L. So, this is d L, do not get confused, this is d small l, okay, d small l, and this total length is L, this total length is L. So, your decrease in intensity is of first order with respect to concentration. So, d I by d t will be proportional to concentration and proportional to this small length, which is d L, small length d L. Minus sign comes because I decreases when it passes the sample. So, now let us integrate this between I naught to I, and that is when length is 0 to length is equal to L. You remember here length is 0, here length is L, and here intensity is I naught, and here intensity is I. So, you are integrating intensity between I naught to I and length between 0 to L. What you will get is log ln I naught by I naught by I. So, this will be, I have taken this minus sign here, and so this will be ln I naught by I. If you integrate this, this will come minus ln plus ln I by I naught, but since I have taken negative sign here, so I can write minus ln I by I naught, and that is nothing but equal to ln I naught by I is equal to k C L. If you take logarithm at the base 10, then log I naught by I is equal to 2.303 k C L, and this 2.303 into k is known as epsilon value. So, epsilon into C into L. So, what Lambert's Beer law tells you, that quantity of light absorbed by a substance dissolved in a fully transmitting solvent is directly proportional to concentration of the substance and the path length of the light passing through the solution. So, I is equal to I naught 10 power minus epsilon C L, this is length, where I naught and I are the incident and transmitted intensity, this length is L. Okay. Now, this we got what, log I naught by I is equal to epsilon C L. This I naught by I is known as transmittance. So, minus log T is equal to epsilon C L, where T is transmittance, look here, and this minus log T is called absorbance. So, your A is your absorbance, and that is given by log I naught by I, log I naught by I. So, if you pass light, intensity of the light decreases when it passes through the solution. But now, what we are measuring is absorbance, which is log I naught by I, and since I naught is always going to be greater than I, and so A is going to have a positive value, A is always going to be positive value. If A is large, it means I is small, I naught by I is large, and since I naught is a constant, and so I is going to be small. So, I is going to be small, then absorbance is going to be high. Intensity of light decreases exponentially as it passes through an absorbing media. So, we have already written that I is equal to I naught exponential minus, if you remember, I naught by I log is equal to epsilon CL, and so let us just cancel this out. So, log I by I naught is equal to minus epsilon CL, or I by I naught is equal to your 10 power minus epsilon CL. That is what we wrote earlier. So, you can see that I decreases exponentially. This is your Beer-Lambert's law. What is that? A is equal to epsilon CL, epsilon CL. This epsilon is known as, which is a constant, molar extinction coefficient. Okay, molar extinction coefficient. It is constant for the absorbing species at particular wavelength, and basically it defines absorption of a species at a particular wavelength. It is a constant for a given species at particular wavelength. So, even if our species is same, the absorbance or epsilon can differ at different lambda value, but for a given compound at a given wavelength, epsilon is constant, and the value of epsilon will depend on the number and type of chromophore present in each molecule of absorbing species. And we have already talked about on what factor intensity in a spectra depends on. Basically, epsilon depends on all those factors. C the concentration of the sample in the cuvette, L is the length of the light path through the sample. And one of the most important property is absorption is an additive property, and this is very important because we will later see that this can be used to know the thermodynamic and kinetic parameter of a reaction. So, absorbance of a mixture of n species will be given by I is equal to 0 to n A I. One of the most important application of Beer-Lambert's law is to get the concentration, and what the Beer-Lambert's law tells you is that absorbance is proportional to the concentration, and so the plot between absorbance versus concentration must be a straight line. So, it is here a straight line, and if you know what is the absorbance of the sample, you can tell what is the concentration, and this line is called your calibration curve, and that is made from standard solutions, standard solution. By standard solution, I mean solution with known concentration, solution with known concentration. So, first you make a calibration curve, and if you know what is the absorbance at a particular wavelength, in an unknown sample, absorption of component, a compound at a particular wavelength in an unknown sample, you can know the concentration by using calibration curve for that compound, But it is not always true that absorbance versus concentration shows you a linear curve. What happens is, at high concentration you can see the deviation, What is this deviation due to? What is limits to Beer-Lambert law or Lambert-Beer's law? The deviation could be due to chemical interaction. At high concentration, deviation takes place from linear behavior or linear deviation from linear behavior in A versus concentration plot is observed. What can be reason? Reason can be that particles are too close and they basically affects each other charges. The average distance between ions and molecules are diminished, and so what that will do is there is more chances of interaction between themselves and that may lead to association. And so, basically effective concentration of monomeric species will decrease. The deviation can also happen because a molecule may interact with solvent, and that can give you deviation. The deviation can also be due to selection of band wavelength. So, suppose I try to absorb within this band. Here you can see there is minimal change in absorbance per unit in wavelength. So, if you go from this point to this point, the change in absorbance is not very high, but if you suppose I take here change in the wavelength will lead to a large increase in absorbance. So, large change in absorbance per unit change in wavelength. So, what will happen if I try to plot absorbance versus concentration for if I measure the concentration in this wavelength range, I will get this kind of curve. But if I try to measure in this band, then I will get a non-linear curve, and it will deviate from a straight line. There will be deviation from a straight line. So, if the band of wavelength selected on the spectrophotometer is such that molar absorptivity of the analyte is essentially constant, deviations from Beer-Lambert law are minimal, and that is what happens when we are selecting band A. However, if a band is chosen such that molar absorptivity of the analyte at this wavelength changes a lot, then the absorbance of the analyte will not follow Beer-Lambert's law. There is another limitation, that is due to use of polychromatic light. So, absorbance of a compound depends on wavelength of the light which we are using to get the concentration or get the absorbance. For example, if suppose this is a spectra of a compound, and if I choose a wavelength here, then your absorbance is going to be high. If I choose a wavelength here, then absorbance is going to be low. Suppose I have a polychromatic light, it means a mixture of certain range of wavelength. What will happen? You can see here there is a decrease, and so what will happen is that your absorbance will be sum of absorbance at this wavelength and at this wavelength or within this range, and so the absorbance will not be high, it will so low. So, let us look at here. If I measure at this wavelength, then I will get this curve. If I measure at this wavelength, I will get this curve, and your absorbance is a mixture of these two, and so there will be deviation towards the smaller absorbance value. What does this mean is the assumption that the radiation reaching the sample is of single wavelength is generally not true. The radiation are generally mixture of wavelengths, and thus they are polychromatic, they are not monochromatic, and because of that what we are observing is a smaller absorbance, and so deviation from Beer-Lambert's law takes place. Even if you take very good wavelength selector, you may not be able to get a single or a radiation of single wavelength. It is always going to be a mixture of few wavelength, and because of that the absorbance versus concentration curve will not exactly follow Beer's-Lambert's law. There are other limitations, and that may be due to the kind of cuvette you are using, and you can look at that there can be. So, let us think about this. What we are measuring? We are measuring the intensity of the light when it passes through the sample, and we are looking at the ratio between I naught versus I. And what we are assuming that the decrease in I is only due to absorbance of light by the sample, but the intensity may also decrease due to reflection losses at interface. So, you see, if suppose the material of the cuvette reflects the light, then your light is not passing through the sample. So, a part of intensity is lost due to reflection. There can be reflection here. So, interface again at the interface, and so there is your decrease in intensity. This decrease is not due to absorption, this decrease is due to reflection. Then what can also happen is that there are, suppose, dust particle in our solution, our sample, they will scatter the light. If there are bigger particle in the sample, they will scatter the light. So, light can be lost by other processes than absorption, other processes or processes other than absorption. In that case, I naught by I is going to be much higher in comparison to when your decrease in intensity is only due to absorption. So, you may see higher absorbance, in comparison to a perfectly normal absorption measurement, So, this is about your wavelength selector. Now, I will also talk about light source. There are two different kind of light source you can use, and one is deuterium lamp. This is basically gives you a truly continuous spectrum in the ultraviolet region, and this spectrum is produced by electrical excitation of deuterium at low pressure, and it basically gives light in the region 160 nanometer to 375 nanometer, and so this is generally used for ultraviolet region. So, this is tungsten filament lamp is the most common source of visible and near infrared radiation. This is your deuterium lamp and this is your tungsten lamp. This already I have discussed. I have already discussed wavelength selector. So, here is the light source. So, light source can either be a deuterium lamp or tungsten filament lamp. Now, I will move towards the application of absorption spectroscopy. So, what we can look at is, if we want to analyze a molecule, here it is a protein molecule. and we have to look at what are the prosthetic group in that molecule. They may have absorption band in near UV visible regions, and these bands are usually sensitive to local environment, and so we can look at even the effect of environment by looking at the spectra of prosthetic groups. So, here are some prosthetic group and their UV spectra. For example, beta carotene, this is the spectra, this is all trans beta carotene. If 9 cis beta carotene you take, it will have different spectra, and cis beta carotene you take, it will have different spectra. And this is your heme group, it has a well known solid band, and there are some other peaks, other bands. So, each chromophore has their specific UV visible spectra, and based on that we can know, you can qualitatively determine the presence of a chromophore. We can also quantitatively determine the amount of chromophore in that solution, So, what determines the absorbance? The absorbance spectrum for a chromophore under a standard condition is only partially determined by its chemical structure. So, it is not always true that only chemical structure determines the UV visible spectra. Environment of the chromophore can also affect the precise spectrum obtained. And what are the different environment you can think of? So, pH of the solution will determine how the spectra of a particular chromophore look like. Solvent polarity, the solvent which you are using to make the solution, or solvent in which your particular compound is there, that is also going to determine the precise spectrum of that molecule, and similarly orientation effect can also determine. So, UV visible spectroscopy is quite often used for qualitative analysis. It is not only used for a structure determination of organic compound, it can also be used for determination of impurities. The presence or absence of particular absorption band at a particular wavelength may be regarded as an evidence for the presence and absence of particular chromophore in the compound. So, I told you that each chromophore has different absorption spectrum. Some may absorb at suppose 500 nanometer, some may absorb at 550 nanometer, some may absorb at 350 nanometer. So, based on that, you can, by just looking at the UV visible spectrum, you can tell which kind of chromophore is present in the compound. So, if suppose you are carrying out a reaction and you got a particular organic compound, first thing you can do is go and take UV visible spectra of that compound, and maybe you can get some idea about what is the chromophore present in that compound. Not only that, it can also be used for the determination of impurities. So, whenever you are making some compound, there are chances of impurities being present in that sample. So, you can tell about impurities by looking at UV visible spectra, because the impurities which are mainly organic compound will absorb UV light of various wavelength, and that wavelength will be may be different from the wavelength at which your product or reactant absorb, and based on that you can tell about whether there is presence of impurity or not. So, UV visible spectroscopy is quite often used for the determination of impurities in organic compound. We can also go for quantitative analysis. I have already told you that absorbance is proportional to concentration. So, if we measure absorbance at a particular wavelength, we will be able to tell about concentration of the compound. For example, vitamin A1 absorbs at lambda max is equal to 325 nanometer. Lambda max is equal to 325 nanometer, whereas vitamin A2 absorb at lambda max is equal to 351 nanometer. So, the presence of vitamin A and vitamin A2 in natural fats of Vis can be estimated by measurement of intensity of peaks at 325 nanometer and 351 nanometer respectively. So, just by looking at absorption spectra and looking at the intensity of the peak at 325 nanometer, which belongs to vitamin A1, or 351 nanometer which belongs to vitamin A2, you can know the concentration of vitamin A1 and vitamin A2 in natural fats. Similar kind of procedure has been used for estimation of ergosterol in fats, anthracene in benzene, carbon disulfide in carbon tetrachloride, and chlorophyll in plant material. So, I have started to discuss application of UV visible spectroscopy. There are a lot of applications, and since now time is over, I will stop here and I will talk about more applications in the next lecture. Thank you very much for listening.